Expanding binomials can be a lot of pain. No one wants to manually multiply and then add like terms. That's too much work. Thankfully, there's a really cool shortcut we can use instead. Pascal's triangle. To construct Pascal's triangle, we start with 3 ones arranged in a triangle like so. Each new row starts with a 1 and ends with a 1. The terms in the middle are the sum of the 2 terms just above it. 1 plus 1 is 2. To construct the 4th row, we begin with the 1s on the sides, and for the middle terms, 1 plus 2 is 3, and 2 plus 1 is 3. That's the 4th row, and this pattern continues. If we stop here and admire our work, we find that we not only have a beautiful and symmetrical triangle of numbers, but also an exceptionally nice roadmap for the coefficients of expanded binomials. What do I mean? Well, notice that on the side, I numbered each row, starting from 0. The row number tells us the exponent of the binomial, whose terms have the coefficients in that row. Thus, the first row, 1, represents the coefficient of a binomial with an exponent of 0. This makes sense. Anything to the power of 0 is 1. So that means there's only one term, 1, and 1 is technically also the coefficient of 1. What about the second row? The second row represents a binomial with an exponent of 1. Of course, this requires no expansion. That's just a plus b. The coefficient of a is 1, and the coefficient of b is also 1. And we can keep going. If we expand a binomial raised to the power of 2, we get this. The coefficients are 1, 2, and 1. Each row in Pascal's triangle gives us the coefficients of the terms in the expanded binomial. Now, besides the coefficients, we also need the exponents of the variables for each term. To do this, we create 2 sets of numbers. First, we count all the integers from 0 all the way to the exponent of the binomial. In this case, that's 3. For the second list, we start at the exponent, 3, and count down to 0. This is all the information we need. We know the coefficients for each term, the exponent of a for each term, and the exponent of b for each term. This technique is extremely useful, especially if we are expanding binomials raised to higher powers, like 5. To begin, we must find the coefficients with Pascal's triangle. Remember, we start at row 0, so row 5 is technically the 6th row. Alright, we have our coefficients. Now, we count down from the exponent, 5. And in the second row, we count up to 5. Nice. Time to assemble each term. The first term will have a coefficient of 1. A will be raised to the power of 5, and b will be raised to the power of 0. We are multiplying, so we can simplify and ignore the 1s. Great. So our first term is done. That's a to the power of 5. Moving on to the second term, we have a coefficient of 5. A has an exponent of 4, and b has an exponent of 1. Good. The third term has a coefficient of 10. A is raised to the power of 3, and b to the power of 2. And we continue this process for each term. 10a squared times b cubed, 5 times a times b to the power of 4, and finally, 1 times a to the power of 0 times b to the power of 5, which can be simplified to b to the power of 5. Awesome. Just like that, we've expanded a plus b to the power of 5. This binomial is pretty simple, but we can use the same technique to expand more complicated binomials like this one. To expand this, we'll simply have to treat each term in the binomial like a single variable. For example, a and b. Now we expand it like we did before. We start with Pascal's triangle to find the exponents of the terms. 1, 3, 3, and 1. Next, we do some simple counting to find the exponents of the variables in each term. And now, it's time to assemble. We have a coefficient of 1, a is raised to the power of 3, and b is raised to the power of 0. That simplifies to a cubed. The second term has a coefficient of 3, a is squared, and b is raised to the power of 1. That's just b. The next term also has a coefficient of 3. This time, a is raised to the power of 1, and b is squared. And the final term has a coefficient of 1, a is raised to the power of 0, and b is raised to the power of 3. Simplified, that's just b cubed. Alright, with the binomial expanded, we must substitute back the original values of the variables. We set a to negative 3x squared, so let's put that back, and b is 2y. From here, it's a simple matter of simplification. And once we clean things up, we get this. Beautiful. That's our final answer. You can use this technique to expand all kinds of binomials raised to various integer exponents. All you have to do is construct Pascal's triangle to find the coefficients and do a bit of counting, and that binomial is yours for the taking. But most importantly, you ought to subscribe. These videos are a lot of fun to make, but they also take up a decent amount of time. So if you enjoy watching these, or if they've been helping you in any way, be sure to hit that thumbs up button and share this with friends. Thank you so much for watching.